In the last video, I went over how to make an online multiplayer game playable in a browser in about 20 minutes or so. The game was made using a serverless approach, which means that you don't have to pay for any server costs when no one is playing, which is perfect for solo indie devs that don't expect their games to be played by thousands of people 24/7. If you haven't seen that video, I recommend clicking the link in the description to go check it out before this video, as we'll be building upon that to make our game have simultaneous turns. In this video, we'll be taking the demo game we made in the previous video and changing it to move all the players at the same time every 10 seconds instead of when the player clicks. The techniques and AWS services we discuss in this video can be used for anything in your game that needs to be executed outside of players initiating it. For instance, you can use this technique to add a turn timer to a card game. This is what we had at the end of the previous video. Haven't touched it since then, and check it out, it still works. Let's also take a quick look at my bill from last month when I made the video. Yep, $0. As you can see, the free tier usage is pretty damn generous for the services that we used. For example, I made 112 Lambda requests in total during the tutorial. You can have up to 1 million requests for free per month. Even then, it's only 20 cents for every 1 million more requests over that. Let's go over a quick refresher of how the game works before we get into implementing simultaneous turns. We built our Unity game to WebGL and hosted it on a website like itch.io. Players load the game in their browser. When the game loads, Unity tells a small JavaScript file to open a WebSocket with our API gateway endpoint. After the connection is opened, Unity sends a JSON object through the WebSocket with a property called action set to join. API gateway reads that the action property is set to join and runs our corresponding join lambda function. The join lambda adds the new player to our players DynamoDB table and returns a list of all the players back to the caller. When Unity gets the returned packet, it instantiates player prefabs for all the players. When the player clicks on the screen, Unity sends another JSON object through the WebSocket, this time with the action property set to move. And finally, our move lambda is run, which sends packets back to all the players that say where the player wants to move to, and then Unity does that. Alright, so what we want to do in this video is to, instead of moving players right when they click, to instead store the value of where they want to move to in our DynamoDB table, and every 10 seconds send out any moves made in the last 10 seconds to all players. There are a few AWS services which we can use to accomplish this, but I'll be viewing this through the lens of a solo developer that wants to utilize as much of the AWS free tier as possible so that I don't pay anything at all. At the end of the video, I'll briefly touch on some of the other options, so you can choose to research those services on your own if you wish. For this solution though, I'll be utilizing AWS's Simple Queue Service, or SQS. SQS allows for up to 1 million requests for free per month, which is more than enough for our use. SQS is a pretty simple service where you can post messages to a queue. You can then add a trigger to your queue so that whenever a new message is added, a lambda is executed. What's useful for us, however, is that you can add a delay to your queue before new messages are added. So, what we can do is create a new queue with a delay of 10 seconds and then edit our join lambda to post a new message to the queue when the first player joins. We can then create a new lambda called round and add a trigger to our queue to execute the round lambda whenever a new message is added. So, when join posts a message to the queue saying that there's a player in the game, there will be a 10-second delay and then our round lambda will execute. Inside our round lambda, we can send out packets to all players saying if anyone has moved and then add another message to our queue. This will then go on in a loop, sending out move updates every 10 seconds until we stop adding messages to the queue. Alright, let's get into implementing. Open the AWS console and select SQS from the Services dropdown. Click Create Queue. We want a first in, first out queue since we want our rounds to only be executed once per message. Name it round.fifo. Here's the interesting part. Let's set our delivery delay to 10 seconds. This is what causes the messages to be delayed before triggering our round lambda. Let's also set our message retention period to 1 minute since we don't care about retrying messages and want to get rid of them as soon as possible if there's an issue. Visibility timeout should be longer than our message retention period as well so that we don't retry, so set that to 12 hours or something. All the other defaults are fine, hit create queue. The next thing we want to do is add a lambda trigger to execute a round lambda whenever a message is added, so we'll need to make that lambda first. Open up the Lambda console page and hit create function, call it round and hit create. For now we'll just leave it returning a success message. More importantly, if you remember from the previous video, if we want to call other AWS services from our Lambda function, we'll need to update the Lambda's IAM role. So, open up the IAM console page and slap that administrator access role onto the new round IAM role. Now that we have our round lambda created, we can add a lambda trigger to our queue to call it when a new message is added. Open your queue page and click the Lambda Triggers tab. Click Configure Lambda Function Trigger and add your new round lambda. To test if it's working, click the Send and Receive Messages button in the top right. We're going to send a fake test message to the queue to see if it invokes the round lambda. Just fill out all 3 text boxes with test and hit Send Message. Now, after a 10-second delay, our round lambda should execute. To check if the lambda executed, you can click the Monitoring tab on the round lambda page to check the invocations graph. You should have a single invocation show up after a few seconds. Click the refresh button a couple times if you don't see it yet. The first thing we need to do is update our join lambda to send the initial message to the queue when the first player joins. So, let's open up our join lambda, and after we scan the DynamoDB table to get all of our players, let's add a message to our SQS queue if the number of players is 0. Create the SQS client from the AWS SDK, and if players.length is 0, then call sqs.sendMessage. SendMessage requires 4 parameters when using a first in first out queue. They are queue URL, message body, message deduplication ID, and message group ID. Queue URL is the URL for your queue. You can grab that from your queue's console page. Message body is just a string you can use to send whatever data you want to your lambda. In our case, the fact that the message exists is the only data we need, so we can put anything here as we don't really need any additional data. I'm just going to put the letter A. Message deduplication ID is a string that will cause a message to not be added to the queue if any other messages have had the same message deduplication ID in the past 5 minutes. We'll just give it the current epoch timestamp here since that'll be unique for any messages not sent in the same millisecond. Finally, message group ID is a way of grouping messages. This is another one we don't really care about, so again I'll just put the letter A. That should be our only change in join for now. There is a potential race condition here where if multiple people join at nearly the same time, we'll add multiple messages to our queue, but we'll fix that later. For now, just add a to-do. Next up, let's change our move lambda to not move our players immediately, but rather store a value in the players table that says where they want to go. First off, we won't be sending a move message to all players anymore. Instead, we'll only be returning a message to the caller to let them know we've accepted their move request. So, we'll need to add an integration response to our API gateway route so that what we return from the lambda will be returned to the caller. Open your API gateway API and select the move route. Click the Add Integration Response button and then deploy your API changes to your production stage. The next thing we'll be doing is making changes to our move lambda, but real quick before that, let's copy paste the code from our move lambda over to our round lambda since that'll end up being pretty similar. Alright, now open your move lambda and remove the API gateway client, the part where we send the move message to all players, the part where we scan DynamoDB for all players, and the part where we create the player object since we won't be needing those anymore. Let's also add a body to our response that will be sent back to the caller. In the body, let's include action move and a new variable called posDest, which is where the player wants to move on the next round. The value of posDest will be the pos they gave us in the input. Since the player entry already exists in the table, we just want to add a posDest variable to that entry, not overwrite the entire entry, so put won't work for us. First, change the put to update and change item to key. The value of key is our connection ID, which is an event.requestContext.connectionID. Next up is the update expression. Update expression is a string where you describe what about the entry you want to change. For this example, we want to set our posDest variable, so let's write set posDest equals :posDest. In update expression, if you're providing a value, you need to use a colon before a variable name, and then provide the value in another parameter called expression attribute values. So let's add expression attribute values and provide :posDest with the value body.pos. That should be it for this lambda. Update your comments to not confuse yourself later if you come back, and let's move on to implementing our round lambda. The overview for this function is to first get a list of all the players, and if there are any players left in the game, update their pos to posDest and remove posDest if it exists. Then send a message to all players with the new positions, and finally send a new message to our SQS queue to continue the loop. So, take out the line where we parse event.body. This lambda is being initiated by SQS, so we don't have a body to parse. Instead, we're given a list of records with the contents of the messages that have been added to the queue. However, we don't care about that for this example. After getting the list of players, add an if statement where if there are no players in the game, return from the lambda immediately. After that, let's, in parallel, check if each player has posDest set. If they do, that means that in the past 10 seconds they have sent a move request and we should move their position. So, set their pos to posdest and delete posdest. Then we can just call dynamodb.put to overwrite their entry. Then, let's update the message we're sending to all players to instead be a state action and include the list of all players. Next, create an SQS client and call sqs.sendMessage to add a new message to our queue. That's it for this function, so update your comments. But if you notice, we're actually in a really scary spot right now. We have a potentially infinite loop where as long as players table has an entry, we will continually run this round lambda every 10 seconds. If for some reason our disconnect lambda fails to properly delete a player entry, then we could have a runaway loop and eventually we'll run out of our free tier lambda executions and we'll have to pay. I have a solution for that, but for now just put a to-do to remind us to fix that later. Now to Unity, a couple small changes are needed to take care of the new movement logic. To start with, when we get an incoming move packet, we no longer expect a player, so change MovePacketInc to have a posdest instead of player. What I'd like to do is when we get a move packet back is to show a marker on the screen of where you will be moving to next round. So I'm going to quickly create a marker prefab. It's just a simple circle sprite colored red. Next we'll update GameManager to spawn the marker when it gets a move packet instead of immediately moving the player. Add the marker prefab to GameManager as well as a reference to the instantiated game object. That way we can move or delete at each round. In move, check if the marker already exists. If so, move it, otherwise instantiate it. In our round lambda, we return a packet with action type state, so we'll need to update WebSocket and GameManager to respond to that. Add state to PacketAction and the new PacketAction to WebSocket's receive method. Create a new StatePacketInc class with a list of players, deserialize it, and create a new state event. In GameManager, listen for the new state event. In your new state method, destroy the marker, then loop through all the players in the packet and get the corresponding player controller from your player's dictionary. Set the dest to the player's pos. Alright, that's it, run your game. Clicking creates a marker showing where you will move to, and then after 10 seconds you'll get a state packet that moves you towards it. Everything's working, awesome. But we still have those two pesky to-dos we left that we need to attend to. Let's start with the issue where if disconnect fails we'll be stuck in an infinite loop since that's the scarier one. The way we'll be solving this issue is by using DynamoDB's time to live or TTL feature. This is a pretty simple feature where you can specify a property in your entry to denote a timestamp of when you'd like your entry to be deleted automatically. When we first create a player entry in our table, we'll add a TTL property for let's say 5 minutes in the future. Whenever the player moves, we'll update the TTL to another 5 minutes from that time. Then, if the player hasn't moved in 5 minutes, their entry will be automatically deleted. That way, if for some reason our disconnect lambda fails and doesn't delete the entry when they disconnect, it'll automatically be deleted after 5 minutes. To do this, open your player's DynamoDB table console page and in the Overview tab, click Manage TTL. Write TTL for the TTL attribute and hit Continue. If you're wondering, DynamoDB streams is something you can use to trigger a Lambda function whenever entries are added, edited, or deleted in your table. It's pretty useful for doing things like sending messages to all players when someone's player entry is deleted, but for this video we're not going to go over that. Now we'll need to add TTL to our player entries, so open up your join and round lambdas. Before both the dynamodb.put calls, add a TTL property with value math.floor of date.now divided by 1000 plus 300 to the player. Date.now returns the current number of milliseconds since January 1st, 1970, and since DynamoDB expects that timestamp to be in seconds, we divide that by 1000, and then we add 300 more seconds to that since there are 300 seconds in 5 minutes. That problem is fixed now. Well, kind of fixed. If a player entry is deleted through TTL, the other players won't be notified, so they'll just have a player game object sitting there doing nothing. But you can fix that on your own by either using DynamoDB streams or, since we send the full list of players back during the state, you can just destroy any player game objects that weren't included in the state packet, but I'll leave that up to you. Mostly I just wanted to make sure no one gets stuck in an infinite loop and ended up using their whole Lambda free tier. Alright, back to the other to-do now. Currently, if there is no one playing, when two people try to join at the same-ish time, there will be two join lambdas running at the same time and both could possibly get 0 players and send a message to our queue. This will cause multiple executions of our round lambda instead of just one execution per every 10 seconds. In order to fix this, we'll create a boolean that tells us whether or not we've already started the game. To store that boolean, we'll need to create a new DynamoDB table called metadata. Key will just be a string called key, and once again, disable autoscaling on read and write. You can set the units to 1 for both since there won't be many reads and writes to this table. Go to the Items tab and create a new item. set key to playing, and add a new property called val and set it to false. We'll be updating val to true when we've sent the first message into the queue, and we'll set it back to false when round finds there are no players in the game. So open your join lambda, and before calling sqs.sendMessage, we're going to call dynamodb.update. Similarly to the update we did in move, we'll need table name, which is metadata this time, as well as a key, update expression, and expression attribute values. I know it's weird that you need to use expression attribute values instead of just writing true in the update expression, but that's the way it be. However, what's different this time is that we only want this update to be successful if val was false before we try to set it to true. To do this, add another parameter called condition expression. You can use condition expression to tell DynamoDB, hey, I want you to throw an exception if this condition isn't true when you go to update this entry. In this case, we set condition expression to val equals :false, and of course include :false in your expression attribute values for reasons. Now wrap that in a try catch such that the call to SQS send message will only execute if the update call doesn't throw an error. If we do catch an error, don't do anything, just continue with the rest of the function. And finally, in round, if there are no players, set playing back to false. There we go, fix the two tricky bugs, and now you have a game that has simultaneous turns every 10 seconds. Again, this technique can be used for doing anything that needs to happen outside of players initiating it. Before I move on to the rubber ducking and the other options I considered for simultaneous turns, I quickly want to go over what's going on under the hood with our SQS Lambda trigger and how that relates to our free tier usage. SQS is entirely a polling-based service. That means that when new messages are added to the queue, it doesn't notify Lambda. Instead, Lambda needs to continually poll SQS to ask if there are any new messages. If you open up your SQS console page and select the Monitoring tab, you'll see that you're getting about 15 empty receives per minute. That means that there is something calling receive message on your queue 15 times every minute and getting nothing back since there are no messages in your queue. The something that is making those calls is the Lambda trigger on your queue. The actual way this works is that your Lambda trigger has 5 threads running at all times. Each of those threads continually calling sqs.receiveMessage on your queue in a loop. When calling sqs.receiveMessage, the thread specifies that it wants to do a long poll for 20 seconds. What that means is that it will sit there for up to 20 seconds waiting for SQS to say there has been a new message. If 20 seconds passes and there has not been a new message, SQS will return an empty response and the thread will try again. As soon as a new message is added to SQS, it'll respond to the long poll with the new message, and that thread will execute our Lambda immediately with the contents of the new message and then start the long poll again. So, 5 threads calling sqs.receiveMessage every 20 seconds. That's 3 times per minute per thread, which is where the 15 empty receives per minute is coming from. If a poll is successful, then another receive message call is made, which is why it'll jump up when there are messages being added. 15 calls per minute, 60 minutes in an hour, 24 hours in a day, up to 31 days per month totals 669,600 calls per month if there is no one playing your game. This comes out well under the 1 million free monthly calls SQS allows. As a quick side note, you can actually temporarily disable the Lambda trigger by calling Lambda's update event source mapping so that your queue is only polling when there are players in your game. But again, I'll leave that exercise to you to take on if you'd like. Now that that explanation is out of the way, let's rubber duck through our code one more time to better understand what's going on at each step. A player loads the game in their browser. Unity establishes a connection with API Gateway and then sends a packet with action join, and API Gateway runs our join lambda. In the join lambda, we first create a new JSON object to hold our new player's data. This includes a TTL property for telling DynamoDB to delete this entry after this timestamp. We set it to the current time plus 5 minutes. After getting the list of all players from our DynamoDB players table, we check if this is the first player to join the game. If so, we try to update the val property in our metadata DynamoDB table with key playing from false to true. If this update fails due to playing already being set to true by another lambda running at the same time, we just continue with the rest of the function. If the update is successful, we add a message to our round SQS queue. We don't care about the contents of the message, so we just set the body and group ID to some garbage values. We also set the deduplication ID to the current epoch timestamp so that the ID is unique and won't be deleted. The rest of the join lambda finishes normally, but in the meanwhile, that message we added to our queue is being delayed 10 seconds due to the delivery delay that we set on our round queue. Before the 10 seconds is up, our player clicks where they'd like to move. Unity creates a packet with action move and sends it to API Gateway, which runs our move lambda. In our move lambda, we simply update that player's entry with a new pos_dest variable that is set to where they want to move. We send that pos.dest back to them in a move packet. Unity gets this move packet back and instantiates a marker prefab at that location. If the marker already exists, it instead moves the marker. After 10 seconds have passed from when we called sqs.sendMessage, the message is added to the queue. Our queue has a lambda trigger set which will run our round lambda when one of the 5 threads long polling for new messages gets a response. In the round lambda, we first get a list of all the players in the game. If there are no players left in the game, we change metadata's playing entry to false and return early. Otherwise, we update the players' positions in TTL in parallel if they have a pos.dest set. We then send the state update back to all players and add a new message to our queue to continue the loop. Unity gets the state update back and destroys the marker if it exists, and then moves each player to their new position, and that's it. Before we go, I'll quickly go over some other options that I considered that you can research on your own. If you remember from my last video, I mentioned that Word2G cost me about 6 cents at the end of the Game Jam month. This cost was entirely due to the fact that I solved the issue of simultaneous turns using the AWS service called step functions instead of SQS. Step functions is actually a very useful service, but unfortunately they do not have a very good free tier. The way step functions works is that you write a JSON object that defines a list of tasks you'd like executed in a certain order. One of these tasks could be to wait for 10 seconds, and another task could be to invoke a lambda. That's what I did for Word2G, I just ran that in a loop. Another, simpler option is CloudWatch Rules. If you open the CloudWatch console page and click Rules, you see that you can easily create a rule that can execute a lambda on a schedule. Bam, done, easy. But unfortunately, CloudWatch rules only work when the schedule is longer than a minute, so that doesn't work for our 10-second rounds. If you do need something scheduled for longer than a minute, like a turn timer in a card game or something, I recommend taking a look at CloudWatch rules to see if they work for you due to the sheer simplicity. And that's all I wanted to talk about in this video. Up next, either a video on multiple game sessions, IAM, or structuring and maintaining large projects of this type. Let me know which of those you're interested in and do the subscribe thing. Okay, bye!